Okay, hello all. Today we start Unit 4, which is exponentials and logs. Throughout this unit, we have a couple of activities to apply some exponential functions and their concepts to. So that's something to look forward to, something to change up the days a little bit. Okay, so let's look at exponential functions today. This should be pretty much review things you've seen before. So if we look at the graph of an exponential function, this is the parent function. So I'm going to leave the base as a. So if we look at a chart, I have x and f of x. The domain of an exponential function is all real numbers. So let's start with -1. We'll go to 0, we'll go to 1, we'll go to 2. So if I just leave that as base a, so this is a to the -1 or 1 over a. A to the 0 is equal to 1. A to the first is equal to a. And then we have a squared. So we can look at that on a graph. If I make my x-axis whole numbers, and I make my y-axis, that has to be 1 because I know that's my y-intercept. Then I'm not going to label my other intervals. So if I graph these points, I have -1, which I'm going to put right here. And that coordinate would be 1 over a. So a fraction. Then I get to my y-intercept, which is 0, 1. Then I have 1a, which will be somewhere here. And then if I go to 2, I would have 1 over a squared, which would be higher. So if I draw that exponential graph, it looks like this. So there's your exponential function. Hopefully you remember an exponential function has a horizontal asymptote, a value that the function approaches but never gets there. So characteristics, I have a horizontal asymptote at y equals 0. X-intercepts, I have none. Y-intercept for the parent function is always 0, 1. My domain is all real numbers, or -infinity to infinity. My range is 0 to infinity. Remember, the parentheses tells you that 0 is not included, but all numbers greater than 0 to infinity. All right, so there's the graph. Okay, so we're going to solve some exponential functions just as review. So you have this option here, where if you notice that your bases are powers of each other, then you can make your bases the same, and then just set your exponents equal to each other and solve. So in this case, 8 is equal to 2 to the third. So I have 2 to the 3x, and I'm going to change 8 to the common base, 2 to the third, to the x minus 5 power. So now if I use my power of power properties on the right, I can set my exponents equal to each other. If I distribute 3, I get 3x minus 15. If I bring my x's to the left, I get 0 equals -15, which is a false statement. So this one has no solution. So this is a quick way to solve if you notice the pieces can be changed to a common base. So for this example, 1 over 2 to 6, well, 6 to the third is equal to 216. So 1 over 216 is going to be 6 to the negative third to the x plus 1. That's a common power that you should be familiar with. 36 is obviously 6 squared to the 5x. So now that I have my common base of 6, I can use my exponent properties and solve the exponents. So on the top here, I get negative 3x minus 3 using my power of powers equals 10x. If I move my 3x over, I get negative 3 equals 13x. So x is equal to negative 3 over 13. Okay, so that should have looked familiar. Always look to see if you can change to a common base. It just makes it quicker. You can apply your exponent properties. All right, so we're going to look at what's called Euler's number. Euler's number is E, which you've seen before. This is pronounced Euler. So he is the one that discovered this number. Okay, so E is irrational like pi. It's also the base of the natural log. What's in your calculator is that ln key. Its most common use is continuous interest. Or continuous growth or decay. All right, so just a little background. Where does it come from? Okay, so if you think about compound interest is typically 1 plus 1 over, if you think about interest, it's the compounding number, so quarterly would be 4, semi-annually would be 2. So we're going to use the value of n here, and we're going to pretend like we don't know when it's compounded. So then if you do that, you have to take it to the power of n. So that's compound interest, basically. And we're going to do this as n goes to infinity. So as n gets bigger and bigger and bigger, what happens? So if I do n equals 1, I'm just going to do a few for you. If I plug in 1, I get 1 plus 1, which is 2 to the first, which is 2. If I plug in n equals 2, then I get 1 plus 1/2, which is 1.5 squared, which is 2.25. If I go to n equals 10, then I get 1 plus 1/10, which is 1.1 to the 10th power, which is about 2.59374. If I go n equals 100, then I get 1 plus 100th, which is 1.01 to the 100th power, which is 2.70481. And then one more time, if I go n equals 1,000, then I have 1.001 to the 1,000th, which is about 2.71692. As n keeps getting larger and larger and larger, that value over there is going to approach the number e, which is about 2.71. So if you just press that E key on your calculator, it's going to give you a decimal. But just like pi, we think of pi as being 3.14. We think of E as about 2.71. Okay, so there's another place that you can see E. I don't know if you've seen factorials. College algebra students, you probably have. But there's a method called factorial. Okay, so what factorial means is if I do 5 factorial, that's 5 times 4 times 3 times 2 times 1. So there's a key on your calculator underneath your math program. That is the exclamation point factorial. So if you do this as a factorial, if I start with 0, I get 1 over 0 factorial, which actually calculates to 1, plus 1 over 1 factorial, plus 1 over 2 factorial. And if I keep going, I'll go up to 5 factorial, that's going to be approximately 2.71. So it's going to approach the same value. It's just a little background about where E comes from. Kind of interesting. Okay, so if we look at a logarithm, hopefully remember that a logarithm is the inverse of an exponential. It's used to solve exponential equations. So if I start with an exponential and I write it e to the x equals y, if I want to find the inverse, remember you switch your x and y, so a to the y equals x, then I can change it to a logarithm, log base a of x equals y. So you can go back and forth from log form to exponential form and vice versa. So these are inverses. A couple of examples, 2 to the 4th equals 16, which is a true statement. If you rewrite that as a log, you have log base 2 of 16 equals 4. The equivalent statements there. 3 to the 0 equals 1. That would be log base 3 of 1 equals 0. Anytime you have a 1 there in the parentheses, that's called the argument. When you evaluate that logarithm, you should always get 0. If you want to do a negative, 2 to the negative 2 is equal to 1/4, which we should know. And I have log base 2 of 1/4 equals -2. If I want to do a fraction to a negative power, say 1/3 to the -3rd, well, that's equal to 27. Be 1 over 3 to the -3. If you switch it up to the top, you get 27. So the original problem would be log base 1/3 of 27 equals -3. So there's many, many logs that you can evaluate without using your calculator if they're powers of the original base. Okay, so we have logs and we have natural logs. So a common log is log base 10. That's the key on your calculator. It's always base 10. So you might have this, just log x. So that's log base 10 of x. If you wanted to solve one or evaluate it, that would have to be equal to 2. Because exponentially, 10 squared is equal to 100. You have natural logarithm, which is base e. The log base e of x is called the natural log. And on your calculator, you have that natural log key, natural log x. One of my pet peeves that many of you know is please don't say ln when you're referring to that. Please use the term natural log. All right, so let's solve a few. Okay, so we're going to determine the exact answer and we're going to round to the nearest thousandth. Okay, so when you're solving an exponential, you need to isolate the exponential part and then change to a log. So I'm going to subtract 4. I'm going to change to a log, so log base 9 of 80 equals 2x minus 3. I'm going to add 3 and divide by 2. So 3 plus log base 9 of 80 over 2, or you could multiply that by 1/2, would make more sense. There's the exact value I want to see. So then you can evaluate that on your calculator. To do log base 9, you have 2 options. You can press the alpha key and use alpha F2, and you'll see an option that says log base. Or you can press the math key. I usually arrow up because it's option A, and option A is log base. So if you press your log base key, you'll be able to put that base 9 in there. Make sure you're using your order of operations correctly, because you want to evaluate the numerator and then take that and divide it by 2. So you might take your calculator and make sure you can get the correct answer for these. I got about 2.497. All right, so this one is a natural base. So I'm going to divide by 3. So I get e to the 2x plus 1 equals 17. I'm going to change to log base e, or natural log. So natural log of 17 equals 2x plus 1. Subtract 1 and divide by 2. So -1 plus natural log 17 divided by 2 is x. There's the exact answer. And if you put that in your calculator, I would use your natural log key. You should get about 0.917. So be careful when you're doing these. If you're going to use your fraction key, that would be fantastic. Or you can evaluate the numerator, calculate that answer, and then just take the answer divided by 2. That's what I do a lot because the fraction key is annoying to me. All right, so this one I have to isolate my 10 to the 3x minus 5. So I'm going to subtract 15. And get -4. I'm going to divide by -2. And I get 10 to the 3x minus 5 equals 2. So now that I have that isolated, I'm going to change to a logarithm. This is going to be my common log, log base 10, so I don't need to put that base 10 in there. So I just get log base 10 of 2 equals 3x minus 5. You got to show me the steps that you're using to get to your exact answer. So I'm going to add 5 and divide by 3. So 5 plus log base 2, or log of 2, over 3 equals x. There's my exact answer. My approximate answer is going to be 1.767. So again, I need exact and I need rounded. Okay, so the last piece of the puzzle today is our compound interest, which is a review as well. So you're going to need to know your formula. All of these things are going to pop up in these activities that I have to do, and then the performance task at the end. You're going to have to know how to do logarithms and exponents and all these good things that we're going to cover. So know your formulas. So this one, P is your principal or your starting amount. R is your interest rate as a decimal. It's how often it's compounded, and then T is your time in years. Okay, so these should be pretty straightforward. You can use your calculator once you write down how you're getting your answers. Okay, so I have my final amount is equal to 7,300 plus 1 or times 1.07. Semi-annually is twice a year. So take that rate divided by 2. And then I need to do my semi-annually times my number of years. So 2 times 3. You should be able to put that in your calculator all as one string. Just make sure you're using your parentheses. And go ahead and do 2 times 3 is 6 as well. So if you do that correctly, you have $8,973.56 at the end of 3 years. Okay, so this one, 13.6%. That is kind of an unheard of interest rate, unless you're playing the stock market, and of course that's going to vary. So for this one, I'm starting with 21,000. My 13.6% is 0.136. Compounded quarterly is 4 times a year. So then I have quarterly times my 4 years. So if you take that, put it all in at one time. Don't try to do pieces. That's why you have the fancy calculators. So $35,854. Oops. And 85 cents. So that 13% really helps you out. After 4 years, you earned what, about almost $15,000 interest. Kind of unheard of. Okay, so this one, we have $3,000 at 6.7% compounded weekly. There's 52 weeks in a year for 10 years, 520 times. So 3,000 times 1 plus 0.067. Make sure you're changing your percentage rates correctly to decimals. Divided by 52 to the power of 52 times 10. That will give you about $5,860.18 at the end of 10 years. All right, so there's some exponential review. Make sure that you are showing your work on these last ones. All I did was show you how I got my answer. On the solving exponentials, make sure you're showing me the exact answer and your estimated answer. Have a great rest of your day.